So now this this over here was the last of the intermolecular forces that we had to study, and in this we have van der Waals forces, which are temporary dipole induced dipoles or instantaneous dipoles, and relatively they're one of the weakest, but they are dependent on size. So if the size is really large, they can be really strong as well, and they're always present even in molecules that have hydrogen bonding or that have permanent dipoles. They're always present. So uh, and I did explain how these arise, these forces. So if you have a molecule like H2, okay, this is what we learned, that if you have a molecule of H2, the electrons are evenly distributed. So it doesn't really have any dipoles, any permanent dipoles at least. But during collisions, the electrons are going to fluctuate randomly. That would result in the formation of temporary dipoles. So they would be bumping around, and temporary dipoles are going to be produced. And those temporary dipoles, for a very temporary instant, this side would be negative. Negative side would repel the electrons. So the electrons are going to get repelled in the neighboring molecules, and that side would become negative. This side would become positive, and so on. So there would be induced dipoles, and the next second the dipoles might switch. There might be another collision, and this side becomes negative and this side becomes positive. So the electrons get knocked to this side during a collision. Now the positive side will attract the electrons from the neighboring molecule, and that would make this side negative, that side positive. So induced dipoles would be formed, and which is why, due to the fluctuating dipoles, there would be some forces of attraction, which would be known as van der Waals forces. So one thing is that they are always present in molecules. Even in molecules that have other intermolecular forces, they would always be present. And size, van der Waals forces, their strength increases when are van der Waals forces stronger? Number one, larger molecules, there's going to be more, I mean, they've got more electrons. If you have a bigger molecule, they've got more electrons. So the sizes of negative and positive charges that are building up, they're going to be larger. Like chlorine has a total of 17 electrons, that's a total of 34 electrons. So if the 34 electrons get knocked to one side, the slight negative charge and the slight positive charge, that would be pretty large. So 34 electrons getting knocked to one side, getting knocked to the other side. Hydrogen just has a total of 1 electron here, 1 electron here. That's a total of 2 electrons. So if 2 electrons get knocked to either side, then the slight positive, slight negative charges that are building up, they're not going to be that strong. So large molecules, they are going to have more van der Waals forces. Why? Because they've got more electrons, which would result in greater slight positive, slight negative charges, even though they are temporary dipoles. And the second factor is that is more of an organic factor. In organic chemistry, you're going to learn about that. Greater surface area, you're going to have more van der Waals forces. What I mean by greater surface area is that if you have a molecule that's, especially an organic molecule that's really big and it's spread out, then it's obviously going to collide or interact with other molecules more, because the shape is such, like it's got a pretty big surface area. So it's going to have more collisions, and more electrons are going to get knocked out. So that would result in the formation of more temporary dipoles and induced dipoles as well. And induced dipoles. So if you have a bigger molecule, the electrons are more spread over a much bigger area. The same molecule could have a lesser surface area if the molecule shape was different. I mean, the size would be the same. except that the molecule is not that spread out. So it's got all these hydrogen atoms. So now the thing is that this molecule is not going to interact with, because the atoms are kind of more close to each other. So they're closer to each other. So it's got lesser surface area. It's more compact. I mean, that one is more spread out. So that one would result in more collisions. There's going to be more interaction with other molecules. Think of this molecule flying around. Because of its shape, it's going to bump into other molecules a lot more. Because of this shape, it's slightly more compact. The atoms are slightly closer to each other. Even though the size is the same, this one over here is going to have fewer collisions. And there's going to be lesser interaction with other molecules. So there's going to be lesser temporary dipole. And I'm just going to write TDID, temporary dipole induced dipoles. Okay, is this point clear? The strength of van der Waals forces. Is this clear? And is this clear, Amna, Alicia?
Yes, sir.
Okay, so that's about it. Okay, we've done 3 intermolecular forces. One of them is van der Waals forces. The other one is the previous one was hydrogen bonding. We talked about that, and we talked about permanent dipoles, which depended on the shape and the electronegativity difference. Hydrogen bonding were kind of the same thing, except they were a lot stronger version of a permanent dipole. And then you had van der Waals forces, and they were always present. The electrons are always getting knocked around. So even molecules that apparently don't have a dipole, a temporary dipole would be produced on them. So this is van der Waals forces. Now, the thing we're going to talk about is, the last thing that we're going to talk about is physical properties that are dependent on intermolecular forces. Like, we studied 3 types of intermolecular forces. So we studied 3 types of intermolecular forces. So physical properties that are dependent on these intermolecular forces. Now, the first one is property number 1 is it's obviously melting and boiling point. That doesn't need any explanation. That if the molecules attract each other strongly, then they're obviously going to be solids, and it would be difficult for them to melt and boil. So that's pretty obvious. The second property that depends on intermolecular forces is the solubility of the substances. Now, the rule is that molecules having same type of intermolecular forces are soluble. Or you can say molecules having the same strength of intermolecular forces are going to mix or dissolve in each other, and they're going to be soluble in each other. Okay, so it doesn't really, same strength kind of translates into the same type of intermolecular force, but not exactly. I mean, the important point is that 2 molecules, if they have the same strength of intermolecular forces, the same size of slight negative, slight positive charges on them, then they're going to mix with each other. And I'm going to show you how. For example, ethanol and water, they mix. The reason they mix is that ethanol molecules are able to attract water molecules. So what type of intermolecular force would exist between ethanol molecules and water molecules?
Hydrogen bonding.
Okay, so it's going to be hydrogen bonding because H is very strongly positive. And because of the extra lone pairs on oxygen, even though it's very electronegative, the negative charge is even stronger because of those lone pairs as well. And the same thing over here. Oxygen has these lone pairs, really strong negative charge over here, and the H is strongly positive. So they are almost attract each other with the same force. So I'm going to show the hydrogen bonds. The negative lone pair will be attracted to the positive H. The lone pair of this will be attracted to the positive H of water molecule. And similarly, just a second. This H will be attracted to this lone pair. The lone pair will be attracted to the H over here. So they'll be attracting each other and they're going to mix with each other. So same type, same strength, they're going to mix. Now I'm going to show you why if the strength is different, why wouldn't they mix? Because mainly one of the reasons is that they're not going to attract each other equally. So for example, I mix. So now, for example, I mix water, which makes really strong hydrogen bonds. It's got those lone pairs, partial negative charge, negative, and there is positive and positive. And I mix it with CCl4, which is an organic solvent. It is tetrahedral in shape. And here are some, I'll just copy a few more molecules. So here's another CCl4 molecule. And here's another water molecule. Let's say I've stirred them around and they've all mixed for a temporary instant. Now, is CCl4 polar or non-polar? Will it have partial negative, partial positive charges? Or are the dipoles canceling out? Okay, what's going to happen? Hani, any idea, Mayim? Which one is more electronegative out of all the four, out of these atoms? Abdullah? Does anyone know if this is polar or not? Alicia, any idea? Anna?
Chlorine.
No, but chlorine, is it electronegative or not? It likes to gain electrons, right? Yes, so all the Cls will try to pull electrons. But I told you that dipoles depend on the shape of the molecule. This is a tetrahedral molecule. If all chlorines are trying to pull electrons in different directions, the dipoles will cancel out. Okay, this is something that we did earlier. That when you have dipoles, I mean this thing. When we were talking about permanent dipoles, I told you that a bond is going to be polar only if there's a difference in electronegativity. Like Cl is more electronegative. So Cl will try to attract electrons towards itself. So the electrons would be slightly closer to Cl. It's going to have a stronger attraction. The elements that are in the corner of the periodic table, they're the ones that are very, very polar. On the other hand, if both atoms try to pull electrons equally, the molecule will be non-polar because the electrons are going to stay right in the middle. So the shape of the molecule mattered when it came to dipoles cancelling out. Okay, this is something that we did. Like if you have a CO2 molecule that's linear, there's an oxygen here and there's an oxygen on the other side. Both of them are really electronegative. This oxygen tries to pull electrons and this oxygen also tries to pull electrons, but the electrons stay right in the middle because the forces of attraction are going to get cancelled out. Same was the case with AlCl3. It was non-polar, even though Cl is very electronegative. CCl4 also the dipoles would cancel out because of the shape. So eventually the electrons will remain evenly distributed because all Cls are trying to pull the electrons towards themselves and the forces of attraction are going to get cancelled out. Okay, is this clear? Clear, yes or no?
Yes, sir. Yes.
So the point is over here, the dipoles will cancel out, which means this molecule will not have any dipoles. It will, although, have weak van der Waals forces. Every molecule has weak van der Waals forces. So water molecule would be highly polar. CCl4 would just have these tiny fluctuating dipoles. Like for very instant, this molecule collides with some other molecule. Electrons might get shift to this side, and the other side would become slightly positive just for a very temporary instant, and then it's going to disappear. Then there might be another collision and the electrons get knocked very slightly to this side. This side would become negative. This side would become very slightly positive. And then that would disappear. So the electrons would just fluctuate around randomly when these molecules are bumping with other molecules. That's it. So it's not going to have very large dipoles. It's going to have van der Waals forces. As I said, I've mixed these four molecules around. Two of them are capable of forming hydrogen bonds, really strong hydrogen bonds, while the other two they just don't have any strong intermolecular force. So the strength is different. So what would happen is, even if I mix them together, what would happen is that the positive H over here will attract the lone pairs of the water molecule. I mean, the water molecule will not be attracted to this. So what's going to eventually happen is that the water molecules are going to get, I mean, the CCl4 would be pushed around. I mean, they're going to be pushed away. And the water molecules would all come together and they would start sticking to each other. So they would all come around and the lone pair of the water molecule will be attracted very strongly to the H positive of the other water molecule. So the CCl4s would be pushed away, which is why separate layers would be formed. The water molecules would all start getting together and they will not mix with CCl4 because they're not going to attract. I mean, the simple reason is they're not going to attract CCl4. So there might be another water molecule coming along, and that water molecule, its negative part will get attracted to the positive H. So they would all start lining up. So this is what's going to happen, that sometimes the liquids will not mix, like oil and water. So what's basically happening when oil and water are mixed together, this is what happens. I mean, this is what happens. Why do they form separate layers? Because all the water molecules, they kind of tend to stick together and they push the oil molecules away. For example, in this case. So that's why they end up forming separate layers, because water is not attracting the CCl4. So the point is that molecules that have, the rule is that molecules that have the same strength or the same type of intermolecular force, they are soluble in each other. If they have different types of, like one of them has van der Waals forces and the other one has hydrogen bonding, they're not going to mix. Is this clear?
Yes, sir.
Okay. So again, now what we're going to do is we're going to start with the past paper questions related to intermolecular forces. Just one second, let me open this is the same worksheet I sent earlier. The atomic structure and chemical bonding worksheet. Again, we're just going to do intermolecular forces questions. So probably this one. So this one, why is the boiling point for ammonia higher than the boiling point of phosphine? The first question. Remember, the simple reason is I told you that hydrogen bonds are formed when N, I mean, you have these highly electronegative elements, O, F, and N, when they're directly bonded to H and the lone pairs are present. So it results in the formation of a very polar molecule. The H has a very strong partial positive charge, and the N, even it's very electronegative, so it has a very strong partial negative charge, which is even stronger because of the extra lone pair, the unused electrons that are present over there. So it's a highly polar molecule. So ammonia is capable of forming hydrogen bonds, which are considered to be one of the strongest intermolecular forces. Phosphine, on the other hand, phosphorus is lower down in the periodic table, so its electronegativity is not that strong. So it's not that polar. So the answer would be B. Ammonia molecules have significant hydrogen bonding. Phosphine molecules, they don't. So which is why they are greater attractive forces, and ammonia is going to have higher melting and boiling points. Okay, is this clear? Sorry, is this clear?
Yes.
As the next one in the question, X represents an atom of chlorine, bromine, or iodine. Which explanation for the variation in volatility down group 17 is correct? Now, this is about chlorine. Remember, chlorine is diatomic. Bromine is also diatomic, and iodine is also diatomic. Are these molecules polar or non-polar? Do they have a dipole or not?
Non-polar.
Okay, it's going to be non-polar because Cl is electronegative, like the other Cl is also electronegative. So they will both be, I mean, the dipoles will cancel out. The electrons would stay right in the middle. Okay, the forces of attraction are going to get cancelled out. So they're going to be non-polar. The only attractive force they're going to have is van der Waals forces. It's the random fluctuation of the electrons when they're bumping around. So sometimes this side is slightly negative, this side is slightly positive. Sometimes the reverse happens. The molecule collides and the electrons slightly get shifted to this side. This side becomes slightly negative, this side becomes, so it's temporary dipole induced dipoles. DDID, van der Waals forces. Now, so it's instantaneous dipole, induced dipole. So what happens to the volatility? Now, chlorine is a gas, bromine is a liquid, and iodine is a solid. So that means down the group, what's happening is your boiling points are increasing. So all of them have van der Waals forces. So why does the intermolecular force increase? We just studied that. Okay, what happens? What happens to van der Waals forces? Just a second, let me. That larger molecules have more van der Waals forces because they've got more electrons. So that if you have more electrons that are just fluctuating around, then the van der Waals forces are going to be greater. So this is what's happening over here. You've got bigger molecules down the group. Which means you've got more electrons. Like iodine has a total of 106 electrons. So imagine 106 electrons fluctuating a bit. So the slight negative and slight positive charges are going to be huge. So the first statement is instantaneous dipole becomes stronger. That is true. Down the group, they become stronger between the molecules when you move down the group. Okay? So that's the only explanation. The next one is this is about period C. We can ignore that. It's talking about the electronegativity. Which graph represents electronegativity on the y-axis? So what happens when you move to the right of the periodic table? What happens to electronegativity? Does it increase or decrease? Do the atoms? TK, it increases.
Increase.
So it's going to be D. TK, that's going to be your answer. This one is, in which pair does the second substance have a lower boiling point than the first? So the first one should have stronger intermolecular forces and the second one should have lesser intermolecular forces. That's one thing I missed over here in the, and we can have a look at the diagram as well. Just a second. This diagram over here. One thing remember about remember we will be dealing with a lot of organic molecules. Hydrogen and carbon almost have similar electronegativities. I mean, they're almost non-polar. Whenever you have a molecule which has carbon, lots of carbon and hydrogen atoms, then remember, I'm going to add this extra point. That carbon and hydrogen atoms have similar electronegativities. And that kind of results in a non-polar bond. I mean, not exactly non-polar, but it's almost non-polar. Even though carbon is slightly more electronegative, but just very, very slightly electronegative. So remember, carbon and hydrogen atoms almost have similar electronegativity. So this bond is almost non-polar. So you're going to consider this as a non-polar bond. So coming back to the question, the first one is C2H6. So C2H6 is, you got C. I said this one, what type of intermolecular forces would it have? Permanent dipoles, hydrogen bonding, or van der Waals forces? Is this molecule polar or non-polar?
Non-polar. Non-polar.
Okay, this is non-polar, so it's only going to have van der Waals forces. Just the random fluctuation of electrons that's going on when it's bumping with other molecules. What about the other one, C2H5Cl? Is that going to be polar or non-polar? I mean, what would Cl do? It's a very electronegative atom, right? So Cl is going to try and pull the electrons towards itself. So this side will become slightly negative, and the rest of the atoms or the entire thing would have a slight positive charge. The electrons would be shifted closer to Cl. Is this clear?
Yes, sir.
Yes, sir.
So it's going to have permanent dipoles, which are stronger. Remember, van der Waals forces only increase in size when the size is bigger. I mean, if I told you that van der Waals forces are the weakest, if in a relative comparison, if the size of the molecule is almost the same. So van der Waals forces are the weakest, permanent dipoles are stronger. So that means this one will have a higher boiling point. So he wanted the second one to have a lower boiling point. So the first option is incorrect. Let's talk about option B. Option B is, there's an O. And remember, when you have O, it's a bent molecule, the shape. Remember, when you're talking about intermolecular forces, focus on the shape. So this one will have, it won't have hydrogen bonding, because for hydrogen bonding to happen, the O must be bonded directly to H. Over here, the O is not directly bonded to H. Instead, it is bonded to carbon. And the carbon is then bonded to H. So it doesn't have hydrogen bonding, but oxygen is electronegative. So this side would be slightly negative. This side would be slightly positive, but not a strong dipole. It's just going to be permanent dipoles. I'm just going to write PD over here. I said, what about this one, ethanol? When O and H are bonded together, what type of intermolecular force exists when O is directly bonded to H?
Hydrogen bonding.
Okay, so that would be hydrogen bonding, and they are relatively the strongest. So it's going to have a higher boiling point. Okay, remember, when I write R, that just means rest of the molecule. Okay. So then you've got neon and argon. Neon and argon are just single atoms. So that means they don't have a dipole by default. I mean, there is no electronegativity difference. There's just one atom and one atom over here. So the only thing that's happening is van der Waals forces, just the random fluctuation of electrons that's happening. Argon has more electrons. It's a bigger atom. Neon is a smaller atom. So argon is going to have more van der Waals forces. So argon will have a higher boiling point. The last one, C2H6, we did C2H6, that just has van der Waals forces. So van der Waals forces are weak. So it's going to have lower boiling point. What type of intermolecular forces would this molecule have? The N is directly bonded to H.
Hydrogen bonding.
So that would be hydrogen bonding. So that's going to have higher boiling points. So D is the answer for this one. But the next is this clear? Okay. And is this clear?
Yes, sir.
Okay, which statements are correct? Which statements are correct? The hydrogen bonds in ice are more regularly arranged than in water. So we did this thing. We did this when we were talking about hydrogen bonding. I told you that just one second. So I told you when we were talking about hydrogen bonds, I told you how ice was formed. I think it was somewhere over here. I told you that water is in liquid state, the molecules are kind of energetic, so they don't really care about the hydrogen bonds because they can overcome the attractive forces. When water molecules are liquid, even though it's highly polar, but the water molecule has a lot of energy, so it can kind of move around. And it wouldn't really care about the attractive forces. It can overcome, it's got so much kinetic energy that it can easily break those intermolecular forces. But when the water molecules freeze and they lose energy, then the intermolecular forces become dominant because the molecule doesn't have a lot of energy and it can't break those intermolecular forces anymore. So the positive hydrogen will keep the oxygen close to it. It will attract it very strongly. And the molecule will not be able to leave. This molecule over here will not be able to leave because it's just not energetic enough. So a crystalline structure is formed and the hydrogen bonds are more regularly arranged, which results in the formation of gaps in between because water molecules have a very particular shape. So the oxygen of one water molecule will be attracted to the H of one. The oxygen of another water molecule will be attracted to the H of the other one. That would result in the formation. There would be nothing here in the middle. So in ice, the water molecules are more regularly arranged in ice. Okay, is this clear? Yes or no? Is this clear?
Yes, sir. Yes, sir.
अच्छा उसके बाद है solidification of water to form ice is exothermic. I mean that's O levels. Like you freeze water, is that exothermic or not? I mean, what is freezing? It is exothermic. I mean, molecules lose energy. And why is it exothermic? Because when you freeze, bonds are being formed. Like previously, the hydrogen bonds were not formed because the molecules were energetic. They were easily broken. But when something freezes, bond formation happens. The molecules bonds are formed between them, so it is exothermic. And pure water is less dense than ice. That is, I mean, that's just general knowledge. Pure water is less dense than ice. Ice floats. Ice has lower density. That's actually going to be incorrect. Water is more dense. Ice is less dense. I mean, ice has gaps in them, so it has lower density. Water molecules are closer to each other. So ice floats on water. Ice has lower density because of those gaps. So which solid contains more than one type of bonding? Remember, when they talk about bonding, whenever they talk about bonding, just a second. So whenever they talk about bonding, bonding represents a chemical bond. I mean, if you use the word generally, bonding refers to a chemical bond as well as the intermolecular forces. So for example, the first one, iodine molecule has a strong covalent bond. The other iodine molecule will also have a strong covalent bond. But in between, there would be van der Waals forces because it's a polar molecule. So there would be two types of bonds. There's going to be a covalent bond, which is going to be a sigma bond. Plus in between molecules, there's going to be van der Waals forces. I'm writing VDW, van der Waals forces. So there would be two types of bonding in iodine. So A is correct. Silicon dioxide will not have two types of bonding because silicon dioxide has this structure. If I SiO2, so SiO2 structure is like this. I mean, this is a good representation. So this is your SiO2 structure. It only has, every silicon atom is bonded to 4 oxygen atoms. Then those 4 oxygen atoms are further bonded to silicon and the structure just continues. And it's a tetrahedral arrangement. It's a giant covalent structure. So SiO2 is sand. It doesn't have intermolecular force. It just has covalent bonds. Everywhere there are covalent bonds. Giant structures, they normally don't have two types of bonding. There's just one type of bonding that's just repeating over and over again. So remember this for giant covalent structures. Except for one giant, I'll talk about that one. Sodium chloride is again just one type of bonding. That's a giant ionic lattice. NaCl will have this kind of lattice. Like, it's going to be a bunch of positive ions and negative ions all attracted to each other. So maybe this one. So it's just going to have sodium ions and Cl ions all attracted to each other. So there would only be just one type of bonding, and that would be ionic bonds. Positive ions attracted to negative ions. This one kind of, just like this. So there would only be one type of bonding. As anyways, zinc is metallic. Remember what is a giant metallic lattice? That is also a giant structure. Giant metallic lattices have, let's take this image. So giant metallic lattice have metal ions. Metal ions, they tend to lose electrons. They all start losing electrons. The electrons are all roaming around in the middle. And so that's what a giant metallic lattice is. It only has metallic bonds. That's it. Electrons, delocalized electrons. It's a sea of delocalized electrons attracted to positive ions. Positive ions are attracted to delocalized electrons. And it just continues. So it only has one type of bonding. So remember, most giant structures, whether it's giant covalent structures like diamond, or whether it's giant ionic lattices, or whether it's giant metallic, they only have one type of bond. That's it. Intermolecular forces only exist in molecules because covalent molecules, simple covalent molecules, because they form independent molecules and they're going to have different types of attractive forces between them. There's one giant structure that actually has two types of forces, and that is graphite. Like if you look at the structure of graphite, graphite is the only structure that has, let's talk about this one. So graphite is the only structure that has intermolecular forces, because they're going to be sheets of graphite, carbon atoms bonded to each other. So there's going to be a bunch of covalent bonds, lots of covalent bonds. There's going to be another sheet, lots of covalent bonds, and there are going to be other covalent bonds as well in this other sheet. But the sheets are not bonded to each other. The sheets will have intermolecular forces, and those intermolecular forces are van der Waals forces in the case of graphite. So remember, graphite is the only one that has, it's only one of the giant structures that has van der Waals forces or intermolecular forces. Is this clear? Anna, is this clear? Amna?
Yes, sir.
Yes.
So now next one, which molecule has no overall dipole? So first one, no, remember he's talking about no overall dipole. The other ones, they obviously, you've got CH3Cl. So the electrons would all be closer to Cl. You've got, and remember, 4 bonds, that's tetrahedral. So again, you've got 2 Cls. So the dipoles are not going to cancel out. The Cl is pulling electrons here and the Cl is pulling electrons over here. CH3Cl, again, the dipoles will not cancel out. Like if you have the H at the top and the Cls are over here, all 3 Cls are trying to pull the electrons downwards. So the bottom side would become negative. It's only in CCl4 where the dipoles would cancel out, and that molecule will be completely non-polar because all the Cls will be pulling electrons in different directions. So the dipoles would eventually get canceled out if you've got 4 Cls. So D is your answer for this. Next one is ethylene glycol is used as a de-icer. It allows ice to melt at temperatures below. Which statements are correct? So ethylene glycol changes the extensive network of hydrogen bonds in ice. So you've got ice, and here's a water molecule, and here's another water molecule. Now in ice, the positive H is attracted to the negative. They're attracted to each other, right? So will the ethylene glycol change the extensive network? So if you add ethylene glycol to it, here is what ethylene glycol is, CH2, and it's got OH and an OH over here as well. So it also has these lone pairs, partial negative, partial positive charges. So what it would do is instead of the water molecule getting attracted to the lone pair of the oxygen over here, the hydrogen bond between the ice might break, because the H positive over here might get attracted to the lone pair of ethylene glycol. So it will change the extensive network of like the water molecules were bonded to each other. They were hydrogen bonded to each other, or they were attracted to each other. But now the water molecules are getting attracted to the ethylene glycol molecules as well. So the extensive network of hydrogen bonds will change. So the first statement is correct. And so ethylene glycol is kind of breaking the attractive forces between the water molecules. Is this clear?
Yes, sir.
And then you have ethylene glycol molecules form hydrogen bonds with the other ethylene glycol molecules. That is also true. Like if you have two ethylene glycol molecules, then obviously they've got the negative and positive sides as well. So, I mean, they can kind of attract each other. So that's true. And ethylene glycol molecule will dissolve in water. I just told you that molecules that have the same type of attractive forces will dissolve in each other. They're going to attract each other. So the third statement, all three of them are going to be correct. And we'll just cover this one very quickly. Which molecule has the largest dipole? So remember, the carbon and hydrogen bonds are non-polar. They don't, they're almost non-polar. Over here, you've got a very electronegative oxygen. So oxygen, being highly electronegative, would pull all the electrons to one side. So this molecule would be very polar. This would be completely non-polar. The carbon and hydrogen bonds are completely non-polar. They almost have the same electronegativity. This one will not have a very strong dipole because it's got all three atoms are kind of electronegative. Oxygen is electronegative. Cl is also electronegative. So, I mean, the electronegativities are not exactly the same, but they will cancel out. So, I mean, all three atoms are kind of electronegative. So the dipoles will cancel out. This one as well, Cl is the one that's electronegative. So Cl will pull electrons upwards. This Cl will try to pull electrons downwards. So again, because of the shape, the dipoles are kind of getting cancelled out. It's only in this one that the electrons will, this one will have the largest dipole. All the electrons will get pulled towards the oxygen. And the other side of the molecule would have a slight positive charge. Is this clear?
Yes, sir.
And here, let's continue tomorrow. Okay, we'll just do a bit more of this, and then we're going to move towards organic chemistry. Okay. Say okay, everyone. Take care. Hafiz.
Allah Hafiz.